Okay, welcome everyone to the 122nd talk of our series. Our speaker today is Sam Miller from UC Santa Cruz, and he'll be talking to us about the tensor product property and the complete prime spectrum in noncommutative tensor-triangular geometry.
Thank you, and thank you for having me. Um, Happy May Day for those who celebrate. Santa Cruz is celebrating it. They're just right on campus. Yeah, I'm going to be talking about something that I've been thinking about for the past month and a half or so. And so I'll be motivating this in two ways to start off. One with non-commutative algebraic geometry, and then the other with just standard tensor-triangular geometry. And I realize this seminar has triangulated categories in the title. We'll be reviewing that a bit as well for completeness' sake. All right, so we'll first start off with non-commutative algebraic geometry. So the question is, so we of course have spec for a commutative ring, and the question is, for a non-commutative ring, what is a suitable replacement, a good replacement for spec? And so one thing we should certainly ask for is that if you have a commutative ring, then whatever this thing spits out should be the same as the spectrum. And so some of the most standard ones are the prime ideal spectrum, which is the collection of all proper ideals, so that are prime, i.e. they satisfy, for instance, that that if you have I times j's contained in P, then this should imply that either I is contained in P or J is contained in P. And this is probably the most standard generalization or extension, but the main issue that it has is that it's non-functorial. But it satisfies almost all of the usual properties that the standard spectrum has. Another version is the complete prime ideal spectrum, which is the collection of all complete prime ideals, i.e. the ones that just satisfy the usual like commutative prime ideal conditions. So if we have x times y is in P, then this implies that x is in P or y is in P. And this one actually is functorial, but it has a separate problem. It actually may just be the empty set. We'll see an example of that soon. And then just one more for good measure, we can take the complete left prime ideal spectrum, and some complete left prime ideals are defined a little more interestingly. We have that x times y is in P, and we have the additional condition that if you multiply P by y on the right, it's contained in P again, then this tells you then that x is in P or y is in P. And this one is sort of a happy medium. One thing that's nice here is that all maximal left primes or right primes are, or sorry, all maximal left or right ideals are necessarily completely left or right prime. But again, this little condition here actually, again, makes things non-functorial. But by what I just said, we also have that this complete left prime ideal spectrum will be non-empty. Perhaps a bigger issue, though, is that actually computing this thing can, in general, be difficult. And so one question we can ask is that, so we've seen all of these are either non-functorial or maybe empty. And so we can ask the question of, does a functorial and non-empty for all rings spectral theory that coincides with spec on commutative rings exist? And Reyes in 2012 answered this. The answer is no. So we can talk about the proof idea. This will come into play at the end of the talk, assuming I have time to get there. So we say that a subset I contained in R is a partial prime ideal if for all commutative subrings C contained in R, we have that C intersect I is a prime ideal of C. And so we can define P spec just to be the collection of all partial primes. And this has the usual or analogously defined Zariski topology. So this, first of all, is functorial. And second, one can show that this is the final object in the category of all functors from ring up to top that are naturally isomorphic to just the usual spec from C ring top to top, although he chose it for set on top, but the same thing holds. Upon restriction to C ring. And 3, P spec, just the matrix ring n of C is the empty set for n greater than 2. And one would certainly hope that this thing is not empty. And in particular, because this thing is a final object in this category of functors, this tells you then that any spectral theory satisfying these conditions is also empty for this class of rings. And so in short, what this tells us is that there is no Goldilocks. There's no perfect spectral theory for non-commutative rings. If you want functoriality, you're just going to have to accept the fact that some of your spectral theories are just going to return the empty set, or vice versa. If you have a non-empty spectral theory, then it cannot possibly be functorial. And so now let's move into the elementary classical TTGO setting. So at least for this talk, I really only want to consider essentially small monoidal triangulated categories or tensor-triangulated categories. What happens in the bigger setting is interesting, but I don't really want to go into there yet, and I still don't have a full understanding yet of how what I'm going to talk about over the course of this talk extends to there. One thing that usually happens in this setting is that when you go to the big setting from the little setting, some theories of supports essentially don't behave quite as well as one would hope. You need stratification and whatnot. So all in all, the point here is that I really want to only consider essentially small monoidal triangulated categories. So let's just recall some definitions. A full monoidal triangulated subcategory I of K is thick if it's closed under taking direct summands, and a tensor ideal in this case if we have that X contained in I implies that X tensor Y is contained in I, and similarly, I'm not assuming symmetry yet, Y tensor X is contained in I. And so in this classical case of K is symmetric, so there's a commuting tensor product, where if you do it twice, you just get the identity back. In this case, a thick tensor ideal P is prime if X tensor Y is in P implies X is in P or Y is in P. And so Paul here in 2005 constructed what is now known as the Balmer spectrum, which we denote by SPC of K. And so this will just be sort of analogously a set of P prime thick tensor ideals. And one has the support. So this is also analogously to the usual support in algebraic geometry. So this will be a set of all P spec of K such that X is not contained. So localization to P does not kill X. And so the complement of supports, so there's a reversal here, form an open basis for the topology of spec K. And so this also, in some sense, defines a support variety where the support of an object is just that subset. And more generally, one can define this category of support data where the objects will be pairs Y, where Y is a topological space, and sigma, where sigma is a map from the objects of K to just closed subsets of Y, which satisfy these sort of standard support axioms. So we have that the support of the zero object is the empty set, the support of your tensor unit is the entire space, support of a direct sum corresponds to union. Given any exact triangle, we have that support of A is contained in the support of B, union support of C, union. Yeah. Shifts don't do anything. And finally, we have that if you take the tensor product of A and B, that's that tensor this corresponds to taking intersections. And morphisms will be just given by continuous maps from Y to Z, which satisfy that they send supports to support. So F inverse of tau of A, the pullback of a support is a support. So the F inverse of tau of A, which will be a closed subset of Z, is just sigma of A. So it preserves the support. And one can note that this is actually a functor, a contravariant functor from the category of all essentially small tensor triangulated categories to cat. And so what we're going to do here is just take some support and just precompose with F. So we'll send it to the same topological space. Just do this. And so Balmer's main theorem is that this pair, spec of K, sup, is universal. It is the final object of our category in our category of supports. It's functorial. And moreover, this can be used then to classify a radical thick tensor ideals. So what this implies is that, or radical means just that x to the n is in I, just implies that x is in I. And so we have this order preserving bijection between the Thomson subsets of spec of K. So these are unions of closed, arbitrary unions of closed sets whose complements are quasi-compact, and the radical thick tensor ideals. Okay, so not only is this thing the final object, it actually is sort of a compression of data. It tells us, in fact, what all of the radical thick tensor ideals are. Okay, and radical is a very mild assumption. For example, if you have if your category is rigid, so if you have duals, for instance, then all thick tensor ideals are in fact radical. And so just some classic examples, if X is an Euclidean scheme, Euclidean in the topological sense, then spec of D perf of X just outputs X. And if G is a finite group, this is extended to a scheme by Friedlander Petzova. The original statement is due to Benson, Carlson, Ricard, and K is a field of characteristic P. Then spec of the Stalo module category of KG is just proj of sort of the classical cohomological support variety. So you take so you consider group cohomology. You take this ring, you take the proj of it. This is sort of like the first example, like the prototypical example of a support variety outside of just purely algebraic geometric setting. Okay, before we get on to the new stuff, are there any questions? All right, so let's move on to non-commutative tensor-triangular geometry. And so this was formally laid out by Nakano, or Dan, Kent Basha, and Milan Yakimov. The paper was published in 22, I think it's from 2019 or so. And this uses a lot of frame theoretic considerations that were pioneered by Juan Krause and Solberg in 2007, and then their companion piece, which added Snashall, that came out in 2020. This was also separately considered by Chris Negron and Yulia Petzova in 23. There's a couple of small differences there that I'll actually touch upon later. And so when our category is non-commutative, so it's a monoidal triangulated category, but not necessarily symmetric or even braided, then a proper thick tensor ideal P is prime if it satisfies the non-commutative primeness condition. So I tensor J is contained in P, where I and J are thick tensor ideals, not necessarily just thick tensor ideals. Implies that one of these is contained in P, and completely prime if it satisfies the sort of element theoretic condition instead. So Nakano, Vasha, Yakimov defined the non-commutative Balmer spectrum to be the collection of primes. And the support is defined the same way as before. It's going to be all x and p, such, or that doesn't make any sense. It's going to be all p in spec of k, satisfying that x is not contained in p. And then you can also define the complete prime Balmer spectrum. And so this will just be all p spec of k, such that p is completely prime. And this will just be, you can just write this as support of x intersect spec cp of k. And NVY go on to show sort of an analogous universality statement. They show that, again, one can consider the category of all support data defined analogously. And they show that this spec k sup is the final object in this category of non-commutative, and there's another addition here. You can either say non-commutative support data, or you can say non-commutative weak support data. And for these two, they're defined slightly differently. I'll say those are in a second. Satisfying sort of the same things. We have that 0 just returns the empty set, 1 returns the whole space, direct sums are unions, triangles give you sort of this inclusion condition, shifts do nothing. And so now the multiplicativity statement changes a bit. So for non-commutative support data, what we have is that we have to take a union over with C running over all elements of K, and this has to be equal to a tensor, C tensor B. For weak support data, on the other hand, it's actually defined ideal theoretically. And so when I say sigma of I, what I mean is the union over all elements in I. And so this will be equal to sigma of I times J. And this ends up being a very nice generalization of the commutative, the standard Balmer spectrum. So again, we have that spec K can classify thick tensor ideals under some mild hypotheses. The classification is a bit different. Essentially, what you do is you have like some support data, and you show that it satisfies some sort of faithfulness condition. So really, only 0 should return the empty set, and it satisfies essentially that every closed subset should show up somehow via the support. And then in this case, you know that this ends up being 1, the Balmer spectrum, and 2, classifying all of the thick tensor ideals. So it behaves a little differently though. Like also we have that spec of K is non-empty, and we have this prime lifting. So if for every thick tensor ideal I, there's always some prime that contains I. And finally, we have that spec of K is a well-behaved lattice, which is partially what gives us this nice classification. But there are some bad things too. The big one being that spec of K is non-functorial. And if you're to construct these categories of support data and weak support data, I made this observation earlier that that is actually a functor. In fact, I believe one can make it a 2-functor. The same does not hold for these categories of non-commutative support data or non-commutative weak support data. And I'll give an example of all of these things soon. Similarly, spec K as a space may not be quite as well behaved as in the commutative setting. So for example, in the commutative setting, we know that the entire space is quasi-compact, and then we know that if you have some support, that its complement is a quasi-compact open as well. This may not necessarily hold in the non-commutative case. And we also may not even have closed points. So we may not know that every prime has like a minimal prime sitting in it. Now I want to advocate for the sort of philosophy here that spec of K, as defined by Nakanobashi and Yakimov, is just one of many different support theories that exist for some non-commutative tensor-triangulated category. And different good axioms of support, whatever that means, yield different spectral. So we always have different spectral theories, but they may yield different universal spectral theories that are worth studying. And this is sort of both analogous to the non-commutative algebraic set, where we have a bunch of different support theories, and the tensor-triangular geometry of big categories, where sort of the usual support axioms that hold for these, essentially small categories, may break down. This is what leads to like stratification in the notion, in the context of like Barthel, Hurd-Sanders, like Balmer-Fabbi support and whatnot. And so we can ask, well, what about this tensor product property? So this is the main thing that I'm going to be concerned with. And so Nakanobashi and Yakimov, in a follow-up paper, show that our pair spec of K support satisfies the tensor product property if and only if every prime is completely prime. In other words, we have an equality between spec K and the complete prime spectrum. Okay. And so I'm just going to say for this talk, at least, that we say any support data that satisfies this tensor product property is a multiplicative support data. And going back up here, you can see that being multiplicative actually implies both of these two sort of weaker multiplicativity conditions as well. And so one thing, so sort of the first statement that I'll make that of mine is that, in fact, spec of K, spec CP of K, sub CP is the final object of S tensor K, which I'm not going to formally define, but you can sort of imagine how it's defined. This is the category of all multiplicative support data, even if spec of K is the empty set. And so in particular, if this holds, this tells you that there is no non-empty multiplicative support for your category K. It is about as non-commutative as you can possibly get. And we'll see an example of this later. Now, this is actually heavily hinted at by Nakanobashi and Yakimov in their paper, but I don't think it's ever formally stated. I should pause here for questions. Any questions?
Can I ask a naive question? So, can you hear me?
Yep.
So, there are examples where, I mean, I'm sure maybe you mentioned them, or maybe you have mentioned them and I missed them. So, where SPC and SPCCP are different. So,
Yeah.
in those cases, I mean, regarding explicit examples of the non-functoriality of the non-commutative SPUC, do we have a correlation between that non-functoriality and, I mean, I seem to remember there was a correlation, isn't there, between that non-functoriality and all primes being completely prime?
So, I mean, if all the primes are completely prime, so I'll show that spec CP is functorial. So if this equality holds, then of course it's functorial. That's a good question. I don't know if spec CP is, well, I guess you have to, it's not quite clear what you mean by functorial in this sense. I guess you can restrict to all categories for which this doesn't hold. And yes, there are certain, I'll give an example later for when spec K is non-functorial. But certainly spec K can still be functorial in some instances. I'm not sure if that's the most satisfying answer.
I mean, I'm sure I'm getting this wrong maybe in some way. I mean, I seem to remember in their papers, Dan Kent and Milan made this point maybe somewhere that in the Buon-Krauser-Solbach paper, uh, they were maybe implicitly assuming in one of their propositions that there was functoriality, but you had functoriality assuming every prime was completely prime. And with these Benson with a spoon Hopf algebras, I mean, they had these nice examples that showed that the tensor property failed, and there were things that were not, there were primes that were not completely prime. I mean, I was just wondering if non-functoriality, if failure of non-functoriality, if finding failures of non-functoriality is somehow the same challenge as finding failures of the tensor product property.
Well, it's so I mean, non-functoriality is like a sort of a very general statement applying to sort of applying to the spectrum, but over all categories. But the complete prime spectrum coinciding with the original non-commutative spectrum, that's just something that applies to one category. So I'm not fully sure how to answer that.
Yeah, I think that's one of the reasons why this is not a very good question.
Yeah. I mean, I guess one could restrict to the subcategory of all monoidal triangulated categories for which this equality does not hold, and then ask, or you can ask, like, is there a subcategory of that for which spec of k is still functorial? And I don't know what the answer there would be. I would guess no, but
Okay.
that would be interesting.
Okay.
Yeah.
Good. Thank you.
Any other questions? All right, so I'm going to take a brief digression, and we'll discuss this tensor product property. Since I've sort of stated it, it looks nice. But well, what relevance is there? So whether this cohomological support of a monoidal triangulated category, i.e., so we can either take the homogeneous spectrum or proj. So we run over all integers I or all positive or non-negative integers I, and we take the Homs in our category from the tensor unit to a shift of the tensor unit. So we'll just denote it by n dot of 1, although usually sometimes we only take the usually we only take the even parts. So this might actually be 2I. So this is indeed commutative and not graded commutative. And we define our support in this way. So we just look at all primes such that the annihilator, so if we have an object X, we look at all primes which annihilate this endomorphism ring. Whether this cohomological support satisfies the tensor product property is also a question of interest. So you can always define this for any finite tensor category. And so the hope is that should, if you define this for a finite tensor category, then the hope is that this should be, or some modification possibly of this should actually be the Balmer spectrum of the stable module category of your finite tensor category. And so Berg, Plavnik, and Witherspoon, they give an example of a finite tensor category without the tensor product property. So this is actually using one of these sort of Benson-Witherspoon-esque type constructions, and they ask the question if every braided finite tensor category that has finitely generated cohomology, this is conjectured to exist by Idenghoff and Ostrich, satisfies this tensor product property. And this, they've shown it for some examples, I believe only in characteristic 0, but it's still very much open as far as I know. So meanwhile, Nakhanov, Vasha, and Yakimov have extended, or more recently extended, Paul's comparison map. So this compares this Balmer spectrum, and so classically it compares the Balmer spectrum and the cohomological support variety. So they extended it to the non-commutative setting. There's a modification one has to make, though. You can't compare the entire cohomological support variety. You have to instead compare the sort of subvariety that consists of the categorical center of the cohomology ring. I won't formally say how that is defined, but it involves some nice like natural commutativity condition. And they conjecture that this is a homeomorphism for all finite tensor categories. And if this were to hold, this would, first of all, imply a positive answer to Berg, Plavnik, and Witherspoon's question. Moreover, if proj ck is a weak support datum, then by naturality, there exists a unique map in the opposite direction. So proj ck spec k. And so one way that you can go about showing that this thing is in fact a homeomorphism, or at minimum injective surjective, is by showing that this thing is sort of an inverse, or a left or right inverse. But of course, this relies on the assumption that proj ck is a weak support datum, and even that holding is not always guaranteed as far as I know. But one can ask the question then, is the image of this map going in the other direction actually contained in the complete prime spectrum? It may be reasonable to expect that this holds, since this is sort of this variety has this sort of nice commutativity condition. And one way that at least I think of the tensor product property is sort of a commutativity-ish condition. And so if this does hold, and you have some finite generation conditions, then this actually implies, plus this being surjective as well, this actually implies then that every prime is completely prime. And so whenever this condition holds, then our spectrum ends up actually playing very well. And I'll talk about that in a bit. So there is this like sort of interesting question of what is going on between this cohomological support variety and the spectrum. I mean, one should expect that at least in some nice cases they coincide. I mean, so perhaps the prototypical example of them coinciding is the modular representation theory setting, which I stated earlier. But it should certainly not be expected in generality. Another point, though, is what should be considered a truly multiplicative support data is not set in stone either. So, for example, Negron and Pitsilva in 23 also have considered support theories for finite tensor categories K, and so more generally, this could be extended to monoidal triangulated categories, but this, at least their work, does need some of the finite tensor category assumptions. So this will so they satisfy that sigma of x intersects sigma of y is equal to sigma of x times y, the usual tensor product property, when one of x or y centralizes all of the simple objects in your finite tensor category. So in other words, you have a braiding, but only for the simples. And this does not necessarily imply then that it centralizes the entire category, although, well, I'll just leave it at that. And otherwise, we just have an inclusion. And actually, over finite tensor categories, although I don't believe it should hold in general, this holds for spec of K. And so then one can ask that if it holds for cohomological support, or something they define, which they call hypersurface support, which I don't want to get too into. And in some cases, they show that actually, yes, it holds for these, and moreover, cohomological hypersurface and the Balmer spectrum all coincide, and moreover, they actually have the tensor product property, not just for this condition, but for all objects. So the tensor product property holds in general. So there's a sort of underlying question of like, when is this holding enough to say that in fact the tensor product property holds? So because in general, it's unreasonable to expect the tensor product property to always hold. In fact, they give an example, I believe, where it doesn't hold, but one can sort of ask for this weaker condition and then go from there. And this approach also has a nice natural extension to big categories that, which, as I've noted for this general tensor product property, we shouldn't necessarily assume that that should always lift to a big compactly generated category, even if its compact part satisfies the tensor product property. Okay, any more questions before I move on? Okay. So now let's just discuss some properties and some examples of this complete prime spectrum. So first thing you would certainly hope to expect is that spec CP, also we have that this sort of this category of support data are both functorial. So if we have a tensor exact functor, f from k to l, then this induces a functor spec CP from f. So it sends a prime q to pull back f inverse of q. And in the same manner as before, we'll send a functor f to y sigma f. One thing that's worth noting here is that this in general will not send Balmer spectra to Balmer spectra. We're not modifying the underlying topological space. We're just changing what the support is. So that's nice. Now we can ask, so any reasonable support data should hopefully sort of, its closed subsets or specialization closed subsets or Thomason subsets should parameterize something. And in this case, they do parameterize something. It's not the nicest thing in full generality, but at least holds. So we have an order preserving bijection between what I'll call dual open. So these are things that are morally should be open under the Hochster dual topology. Formally, what they are is they are arbitrary unions of closed sets that are of the form support of X and radical thick tensor ideals of K that can be written as intersections of complete primes. We have that every intersection of a complete prime gives you a radical thick tensor ideal. However, the converse is not known to hold. I can't find any counterexamples where this doesn't happen, but it doesn't seem like every radical thick tensor ideal should always be in an intersection of complete primes. The obstruction here is that one needs a notion of prime lifting to construct for this bijection. The proof of this, as do the proof of a lot of things that I've discussed here, almost follow or usually follow sort of the exact same as Balmer's original proofs. Sometimes there's some modifications you need to make because of non-commutativity, but a lot of the things really just go almost verbatim. Not really doing that much that's brand new here. And in this case, if spec of k is actually equal to spec CP of k, then this actually becomes then the classical statement from Balmer 05 that we have that Thomason subsets of spec of k are in order preserving bijection with just the radical thick tensor ideals of k. And so if we have this equality that spec k is equal to spec CP of k, then not only is spec k functorial, it has all of the usual properties that one would expect of the Balmer spectrum. For example, it does have minimal primes. All the quasi-compact opens are complements of supports, and that's how every single one shows up. And we have that spec of k is Noetherian if and only if every closed set is a support, and so on and so forth. There's a lot of properties. I don't feel like listing them all, but things essentially work very well and look very similarly to sort of the classical case. And so this is, in some sense, the closest to commutativity that we could get when this holds. And this is known to hold in a variety of cases over mostly the cases we know it holds are finite tensor categories that arise from considering representation category or stable module categories over some Hopf algebra with some nice properties, but more are being computed as we speak.
Sorry, I have a question right now. So, suppose you take a finite tensor category and suppose that SPC of k is equal to SPC CP of k.
Yep.
So, does the Balmer spectrum then identify with the project of the cohomology ring? Do you, do
I
you
don't
actually
know.
have to? Yeah, I mean, it would be interesting to see if that theorem still held.
Yeah. That's one thing to explore.
Because
So
because it should be close to the commutative situation.
yeah.
And you would think that you wouldn't need to take the central cohomological support to do things, but in this case,
Yeah, that's a very good question. I don't know, and I don't think I have the intuition to even wager a guess. That's yeah, I'll look into that.
okay.
Thank you. And so this classification is a partial converse, so it's sort of just an alternate method for determining spec of k and classifying tensor ideals. So in their situation, they work under mild hypotheses. So for instance, you have that spec k is the compact part of some bigger compactly generated category. And so what happens here is if one has a support datum that satisfies these faithfulness and realization properties, then it necessarily must be the universal support. Actually, I have a question. Maybe I'll say this for later because I'm running a little short on time. So one example that we can work in that's been mentioned earlier are these cross product categories, which go hand in hand with these Benson-Witherspoon algebras. So if G is a group acting on K, then we have a tensor functor from G, where we just set the objects to be all the elements of G and morphisms as trivial as they can possibly be. And the tensor product will then correspond to group multiplication. So we have a tensor functor from this to the tensor exact automorphisms of K. This leads to the cross product category K of G. So our objects will be sort of these Deligne tensor products of X and G, where their product will be X. So I'm just going to denote the G action by uppercase G, GY, tensor GH. And so morphisms, so this will be, so we can ask what these are. This will be the empty set if G is not equal to H. And K XY if G is equal to H. Actually, in the paper, I was referencing the set 0, but I think the empty set makes the most sense. And so this is our prototypical example for categories which don't satisfy the tensor product property. Pretty much almost every single example that I know of is this category in some form. So for example, if H is a Hopf algebra and G is a finite group that's acting on H, then one can form the smash product of H smash KG. And the dual is what we refer to the Benson-Witherspoon algebra. And we actually have an equivalence of categories that the stable module category of H cross G is isomorphic to the stable module category of, you take H dual smash KG and then take the dual of that. So Berg-Plavnik Witherspoon show that the cohomological support of one of these categories may not have the tensor product property. We give an explicit counterexample. And Nakano, Vasho, Yakimov show that the spec of K may not have the tensor product property using one of these Benson-Witherspoon algebras. And so Huang and Vasha show in a more recent paper that we have a homeomorphism. So they classify what all the primes are. Between spec K cross G and G spec of K, where G spec of K is the set of G primes. So they're thick tensor ideals that are G stable. And moreover, we have an inclusion I tensor J in P with its usual primeness condition. I is in P, J is in P for all G stable. It is an invariant under G conjugation tensor ideals. And so note, because we're only checking these for G stable tensor ideals, these might be G primes of K may not actually be primes in the usual sense. And so this will come into play. And so what I've shown is that this can also be used to determine the complete prime spectrum. So we have, this actually restricts to another homeomorphism. That's backwards. Spec CP of K and G spec CP of K. And so in this case, so we may have that a G prime is not necessarily a prime, but every G complete prime is indeed a complete prime. And so now we'll come to our example of.
You don't need a G on the left hand side.
Oh, yeah, sorry.
Sorry, Ken, were you going to ask something?
I'm sorry, what was that?
No, I thought Ken was going to ask a question.
No, I was gonna ask the same thing.
Okay.
And so for our example of things where everything breaks down, let's just set K to be equal to the derived module category of K plus itself, where K is a field. So one of the simplest categories you can cook up. So C2 acts on this category by permuting indices, just swapping things. And so spec of K will just be these 2 points, P1 and P2, and neither of these are G stable. And so in this case, we have that G spec of K is just going to be one thing, it'll be 0. And so note in this case that 0 is not a prime, but it is a C2 prime. I guess it should be C2. And so in this case, we have that spec of K cross G. So this will be two things. It'll be 0 tensor 1, and 0 tensor, let's write -1. And so this is because this is not a prime, it is necessarily not a complete prime, since complete primes are primes, and therefore this is also not a complete prime. One way you can see this as well is seeing that there are a number of elements that are not these elements in here that are nilpotent of order 2. You just multiply it with itself, you just get 0. And so necessarily then we have that spec CP KG. Oh, too early. Is the empty set, since this is only one element and this is not complete prime. And I can also give some examples of non-functoriality as well. We have this inclusion from K to KC2. This will just send X to X box 1. And so to note this prime by Q, F inverse of Q will just be 0 in K. I've written down what the primes are in K. There's P1 and P2. So this will be like 0, whole thing, 0. This thing is not prime. And so therefore, since the pullback of F inverse of a prime is not a prime, at least with this way of formulating our functoriality, spec is non-functorial. And one can also check that similarly if one looks at the category of supports and looks at the precomposition by F, this also is not well defined either. So yeah, so here's our concrete example of where the the non-commutative Balmer spectrum fails to be functorial. On the other hand, while working with complete primes, since this is functorial, we can ask, when is this injective or surjective? And so the easy case is when is injectivity. So if F is essentially surjective, then in fact, actually, this is well defined. And both of these induced maps on spectra are injective. The harder version, though, is surjectivity. And in this case, we need an additional condition which we call duoness. I can't say duality because that already means something else. So we say that our category K is duo if left, right, and two-sided thick tensor ideals coincide. And Nakano-Basho-Yakimov proved that this actually implies that all primes are completely prime. And one way that this occurs, for instance, is if you have that every left or right thick tensor ideal has, for every element M, its dual is also in that same ideal. And so this also is shown to hold in some cases. For instance, stable module category of A, for A, any finite dimensional Hopf algebra whose cohomological support is the Balmer spectrum. This can just, if you put together a couple different theorems in the Kanabasha-Yakumov's original paper, this happens. It's unknown, at least to me, if the converse holds. If you have that the spectrum is the complete prime spectrum, then your category is duo. But you can show that it holds under some additional technical assumptions that I don't know how to get rid of, and also that you have that your spectrum is sort of well behaved. And from there, we can sort of carry out the results of a paper by Paul from 2018 on on surjectivity in tensor-triangular geometry. So if f from k to l is an exact tensor functor, so if k is rigid, so it has its duals, and l is duo, and f detects tensor nilpotence of morphisms, so f tensor f tensor f tensor f eventually becomes the zero map, then our induced map on spectra spec CP of f is surjective. And moreover, if f admits a right adjoint, then the converse holds too. Then these are equivalent. So this involves essentially what goes on here is, again, sort of taking the original proof, modifying it for a slightly non-commutative setting, and then just going through the same thing. And this holding is actually a bit of a surprise to me, because usually nilpotence or tensor nilpotence will be much less well behaved in a non-commutative setting. But in this case, some things do actually break down. For example, this statement normally does have a converse, but one needs the stronger condition here. But everything still ends up working out in the end. Okay, so I've got a few minutes left, and so I should have enough time to talk about universality and sort of circle back to the intro. I should maybe pause for questions before I do that, though. All right. So circling back to the intro, we can ask the same question: is there a universal functorial spectral / support theory? They kind of go hand in hand, coinciding with the usual Balmer spectrum for all tensor-triangulated categories, or essentially small TT categories. So we can just kind of lay out the blueprint follow the blueprint that's been laid out by Reyes. So we say that a full subcategory P contained in K is a partial prime tensor ideal for all braided subcategories. So we'll do braided and not symmetric here. I don't know if one can say symmetric. C contained in K. And so one thing I want to specify here is that we're not assuming anything about fullness or thickness, or sorry, thickness or any, actually no, thickness, fullness or anything. We're only looking at just braided subcategories, nothing else. We say that we'll say that it's prime if P intersects C is a prime thick tensor ideal of C. So it's sort of the analogous definition. And one can show then that P is a partial prime. So, well, in this case, I should be a little careful. P is full, but C may necessarily not be, and in many cases won't be. So P is a partial prime if and only if for all commuting A and B, we have that sort of our thickness condition holds, but only for commuting elements. And so commuting just means A tensor B. There exists an isomorphism between A tensor B and B tensor A. I don't want to say anything else about the isomorphism though. Similarly, for all exact triangles with A, B, and C pairwise commuting, if A and B are in P, this implies that C is in P. You can apply shifts to get the other two as well. P is closed under shifts. And then similarly, for all commuting A, B, and K, then A tensor B in P is equivalent to A is in P or B is in P. And the key insight here is that every commuting A, B, and K belong to some almost necessarily non-full braided monoidal triangulated category of K. And similarly for every triangle with A, B, and C pairwise commuting, you can sort of cook up this kind of ad hoc subcategory that contains this triangle and really only this triangle. You'll have sort of the trivial ones or like tensor extensions of it, but that's about it. And so therefore what we get is every coherent choice of primes, so coherent meaning that if we look at the intersection of this prime with a smaller subcategory, then it will remain prime. For each braided subcategory, C of K determines a unique partial prime. And so we can let P spec just be the set of all partial primes. And it's not so hard to show then that P spec is functorial. And sort of by this characterization here that every coherent choice of primes for every braided subcategory determines a unique partial prime, we can write P spec as the inverse limit of just the usual Balmer spectrum of C, where C runs over all braided subcategories of K. And with a little work, we can show then that P spec is indeed this final functorial spectral theory that coincides with spec on braided categories. And so actually, a little more formally, what this is saying is that P spec is the right con extension of spec, sort of along this inclusion from commutative, oh my God, not commutative rings, from TT cat to MT cat, where this will be spec, this is just inclusion, and this will be P spec. And so P spec is universal in this sense. But we can ask the same question now, is it universal in the sense that it is the final support datum for some category of support datum under some axioms? And the answer again is yes. It is the final support datum in quotes, because these are maybe not the most reasonable support axioms for support datum Y sigma that satisfy, again, the same 0 is empty set, unit is the full space, A plus B should be equal to sigma of A, that should be the union, sigma of B, but in this case for AB commuting. And similarly, we have an inclusion here for triangles A, B, C, shift A, where they all pairwise commute. Shifts don't do anything. And then we all have the tensor product property holding again, but again, only for AB commuting. But at present, we do not know if there's a monoidal triangulated category if you put it into P spec, it spits out the empty set. And one can sort of cook up these weird, sort of not really triangulated, but technically by definition triangulated categories where you have all the elements are the elements of a ring, addition corresponds to direct sums, multiplication corresponds to tensor products. But in this case, the prime thick tensor ideals won't be very interesting. They won't coincide with the usual tensor ideal, the usual multiplicative ideals of your ring due to the fact that they are thick. So almost every single prime, there's really only one prime thick tensor ideal, and that is just the 0 object. Wait, is that? I might be getting ahead of myself, but the point here is that the prime thick tensor ideals of this sort of weird triangulated category will not coincide with the usual tensor ideals. So one can't just categorify MNC in that sense. One has to go about it in a slightly different manner. I would certainly expect, though, that there is some category for which this holds. And that is all. A little over time, so thank you all for tuning in. Thank you all, especially on the West Coast, who got up as early as I did. Yeah, any questions?
Thank you, Sam. Yeah, if you have any questions for the speaker, ask them now.
Yeah, so do you have examples where you can compute this P spec?
No. So one interesting question is if you have that the regular Balmer spectrum and the complete prime Balmer spectrum coincide, will these actually coincide with p-spec? I don't expect the answer to be yes in general, but it's possible. This is so when I was writing about, if you read my abstract carefully, you saw something about obstructions, and that was earlier in this week when there was an obstruction, but I think I've overcome that obstruction now. So this is all very new within the past couple of days.
Okay, thanks. Any other questions?
Yeah, so excuse me, in your definition, you have this the C's. Could you those subcategories C, they have to be triangulated, right?
They have to be triangulated, but they don't necessarily have to be full. And so really by
And how
like
do you, I'm confused how, I mean, not confused, but I'm interested in how you cook up a subcategory generated by two objects. You said that very quickly at some point.
Yeah, actually, this was the thing that I was hung up on. So basically, you take the subcategory that where was that? You take the subcategory that is generated by objects by looking at all direct sums and tensor products of these objects. And then for the morphisms, you only take zero maps and isomorphisms. And so necessarily
not full.
Right.
Okay.
Yeah, and like no, this is really ugly.
tricky.
You don't normally want to consider subcategories like that, but all that matters is that this is a genuine subcategory and that its inclusion is a monoidal exact functor. And that's all you need.
But
So
you also know the three morphism in your triangle or something. But that you can just do that. Is that what you're saying? You can.
Yes. Yeah.
You can do a triangulated category which has only one, one triangle.
Yeah. So it's
Very
triangulated for the dumbest reason imaginable. Is that there basically are no interesting triangles. It's only zero maps and isomorphisms. Yeah, it's.
But if you have I'm confused because if you have a tensor, you still have the tensor square of your map, no?
Yeah, but that should.
So what's the triangle on the tensor square of the map? That
Well,
is
it'll
not.
still be an isomorphism, so it'll still be isomorphism 0.
No. I mean the map in the map A to B.
The map 8.
Yeah, maybe it's a technical thing which is no point in discussing here, but you see what I mean? If you want a tensor category which contains a triangle, it has to contain all the tensor power of the maps that you have there and the product.
Well, the tensor power of the map should still be an isomorphism, though.
No, but the map from A to B is not an isomorphism.
Well, it'll be a zero map.
Sorry, maybe I'm not.
So from A to B to B to. But no, I'm confused now.
I thought you were able to produce it when you have a triangle ABC.
For the second one. Okay, yes. In this one, you also include the morphisms from A to B, B to C, C to A, and then there's shifts, and then you can include all isomorphisms and zero maps. So there'll be
but the map from A to B, you would also need, if you call it alpha, you will need alpha tensor alpha.
You also have to include alpha squared, alpha cubed, and so on.
Right. So but the thing is, I don't know how to build a triangle on alpha tensor alpha just from the triangle on alpha. There's an octahedron or something. So yeah, I mean, it just need some inspection. But
yes, this requires scrutiny.
Yeah.
One might have to change it so you just like kind of stay at the very sledgehammery condition of every triangle that is contained in some subcategory, some braided subcategory or something.
Yeah.
So that would be like the formulation where you know it works.
Okay, well, you change a bit then. Yeah, the example where functoriality fails is a very basic example with this C2 acting on two copies of derived categorical field. So it sounds like it's going to kill every attempt of the following form. But I was wondering if there was any hope of limiting in the non-commutative setting, limiting the class of the class of monoidal categories or the class of functors that you allow between them to recover functoriality. Is that a reasonable for the prime spectrum? So
yeah, for the prime spectrum,
I guess it might be a question for Dan and Kent.
I've been thinking about this. All I know is it works for essentially surjective, but that's about it. I mean, that one, is just injective. So.
Yeah, essentially surjective was the only condition that I've seen.
Yeah, that's really a bit harsh to only limit to those, right? Yeah. Thanks for the talk, buddy.
Thanks for listening.
Any other questions?
For this P spec, is there any kind of precise relationship with like spectra of Drinfeld centers? I mean, so Drinfeld center, kind of like I mean, at least for finite tensor categories, it's braided category with some universal property. So
yeah,
if you're looking for something kind of universally commutative.
Yeah, I don't know. Yeah, it's possible. Yeah, but I mean, I haven't thought about that. I would certainly wager that there's that universality gives you some connection there, but I don't know what it would be off the top of my head. That's a good question, though.
Any other questions? Okay, if you don't have any more questions, let's thank Sam once again. Thank you all for coming. We have Dominic Kirstein from Bonn next week.